Um, so the idea is, if you have your 5 switches, you can pick two. There's a number of ways you can pick 2 of them to be down. It's the same as if you have 5 friends. It's the number of ways you can pick 2 of them to join you to go to the movie. And similarly, to connect it to the Mississippi problem, if you have your 5 friends, Alice, Bob, Cindy, Dan, Evan, you can think of just like the word here. The word would be no, no, yes, yes, no, right? So there's a very strong connection between combinations, or there's equivalence rather, between combinations and um, uh, the Mississippi problem with 2 types of letters. The 2 letters are yes, you're invited, no, you're not invited. Yes, Y and N. Does that make sense? Please hit yes if you see the connection between the 2 different ways of thinking about it. And it's a very, very powerful idea. I'm pausing here because we're gonna have this mindset that there's different ways of thinking about combinations and counting that, depending on the context that you're in, it's really, really powerful to recognize which one you're doing. So okay, for number 5, I'll just kind of mention it really quick because I think we did it last time. So just if you need more details, you can watch that video. But for trees, in order to start with a consonant and end with a vowel, first focus on the restrictions. So there's only 3 consonants. So the first option is the first kind of category for the first letter. You have only 3 options. The last one can only be an E, so there's only kind of 1 option. So they put a 1 in the last spot. And in the middle, you have 3 letters left. You just do 3, 2, 1. So the answer would be 3 times 1 times in the middle 3 times 2 times 1. Okay, I want to go through also number 13 is good. Let's do that one. Oh, number 9. Okay. Yeah, I'll discuss a little bit of number 9. Number 9 is a fairly challenging one. And I'm just going to also, I want to mention it because there's a notation in here that I didn't get to show you. So the first is notation. So if you see the letter P, that means permutation. So it's like 7P3. This means how many ways are there to pick 3 people to assign 3 medals, gold, silver, bronze, to 7 people. So there's 7 for the first person for the gold, 6 for silver, and 5 for bronze. This will be 7P3. If you did, for example, 10P4, this would just be 10 times 9. You do 4 spots, 10 times 9 times 7 times 6. Okay, so these are permutations. And in fact, do you guys agree that NPN, based on this, should just be the same as n factorial?
Is that n time or n to the power of p times n, or?
No. It's the P stands for capital P stands for permutation.
Oh, okay.
Yeah, it's not a exponent. It's actually the numbers are subscripts when you write it out. C is combination. So like 10C4, which I don't like this notation too much. I actually like to use this one, 10 choose 4. This stands for, it's similar. It's 10 times 9. Oh my God, I'm so sorry, guys. I'm just out of it here. This is not a 7, 6. This is an 8, 7. 10 times 9 times 8 times 7. but we're dividing in the denominator by the rearrangements of those 4 friends. So 10C4, the key idea between the two of them that's really useful to know is 10 choose 4 is like pick a group of 4 out of 10. You don't care how they're ordered. You're just picking 4 of them. 10P4 is like you want to give somebody first place, second place, third place, and fourth place out of a group of 10. So the order in which you pick them does matter. That's the key distinction. And that's why the 10C4 has a dividing by 4, 3, 2, 1 in the bottom. Okay. Please hit yes if that notation makes sense, what the P stands for and what the C stands for. And know if you have any question also. Any. Oh, yes. Anyone who said, oh, you have any? So permutation is when the numbers are in order. Yes. So I would say permutation. Like, so do you agree that asking like, hey, how many ways are there for if there's 10 people and I'm only giving out first place, second place, third place, fourth place, how many different ways are there for the people to finish the race or something like that? Well, there's 10 people that can get first, 9 people that can get second, and so forth. So that's when you care about the order in which they finish. But if you want to say how many ways are there for the people to get into the top 4, and you don't care what order they're in the top 4, then it would be the combination.
So
Yeah.
how do we go about that or incorporate the equation from question 9?
Yes. I'll get to that in a second. So the other question is, are you okay with this fact? NPN is n factorial. Please hit yes if that makes sense. And no if you're kind of lost on why that works. Because it's like there's n people and you got to go all the way down, so you have n spots. So when you write it out, it's just going to be n factorial. And there's another formula as well, just to kind of be aware of. Do you guys see that one way to think about this is it's actually the same thing as 10 factorial, but all you're missing is the first 6 numbers. So this is actually equal to 10 factorial divided by 10 minus 4, which gets you to 6 factorial. So it's essentially like you're going down 4 spots, which is equivalent to saying take 10 factorial, cancel out the first 6. That will leave you with the 4 numbers counting down from 10, or cancel out the last 6, like 1, 2, 3, 4, 5, 6. So this is really important to understand this problem. Do you guys agree that 10p4 is the same as 10 factorial over 6 factorial? Any questions on that? And I'm happy to explain that in more depth or kind of do more examples. So please stop me if you have any questions. Good to move on here? We're subtracting, so very good question. We are just subtracting because if I want to count down 4 spots, that means that I want to get rid of the 10 minus 4, which is 6, the 6 spots on the right. So I want to only include 4 spots, so I go 10 factorial, but I divide by 6 factorial to get rid of the other 6 that are going to be continuing. Did that clear up why we're subtracting them? It's kind of like the remaining numbers that I want to clear out. Okay, and for example, this would be 7 factorial. Yes, Diana. You'll see why in a second. It is 10 factorial over 6 factorial. But I'm just doing this way because I want to show you the pattern that the way we got 6 is because we subtracted 10 minus 4. But you're exactly right. It's just 10 factorial over 6 factorial. Okay, now let's go to the problem. Because the problem, you have to think about it a little bit, and you're going to have to use this observation that we made. So in the problem, it's n factorial over 10 is equal to n minus 1 p n minus 3. And this is a little bit confusing, n minus 1 p n minus 3. 7p3, sorry, about 7p3 is similar to 10p4. Yes, yeah, 7p3 would be 7 factorial over 4 factorial, because it's 7 times 6 times 5. Is that what you meant? Okay, good. So n minus 1 p n minus 3, it's a little bit tricky. So one thing you can do is you can kind of use this pattern. So this is actually going to be equal to, by the way, n minus 1 p like 3, that's pretty easy. That's just n minus 1, n minus 2, n minus 3. So this thing, if I did it like this, that would be really easy, because I can just list out the three spots, and put in, count it down from n minus 1. So but this time it's n minus 3 spots. So it's going to be a little bit confusing to think of it, but essentially you're not going all the way down to n minus 1. You're leaving off 2 and 1. So what you observe, if you want to do it the way that using the pattern, you can just plug it in and think about what it represents. It's basically n minus 1, but you're not doing the full thing. You're going to leave 2 spots. You're going to do n minus 1 minus n minus 3. And I don't mean to confuse you when I'm writing this. All this is if you're doing n minus 1, which is like, let's say 100 is n minus 1. Let's just say it's 100. N minus 3 is 2 spots less. So like 100, for example, 100 p98, that's basically 100 factorial. But all it is 100 times 99 all the way down to 5, 4, 3, but it doesn't go down to 2 to 1. You've got to cancel those out. So in other words, you could write it as 100 factorial over 2 factorial. And so it turns out you can do the same thing here. This is just going to be n minus 1 factorial divided by 2 factorial, because what you're saying is you're canceling out the last 2 numbers, the 2 and the 1. So any questions on the reasoning for this formula, that n minus 1 p n minus 3 is n minus 1 factorial over 2 factorial? What do you guys think? Does that make sense? I know it can be a little bit confusing there, but how many of you feel like you got that?
I'm kind of confused where you got the 2 from.
The 2 is because, do you see that n minus 1 and n minus 3 are only 2 apart?
Yeah.
So those are 2 numbers apart. If I had n minus 1 p n minus 1, that would be just n minus 1 factorial. But what this is saying is you're not going all the way down to 1. You're just stopping 2 short, because this is 2 less than n minus 1.
Oh, okay.
It's exactly like 100 p98. It just means you stop at, you're going to do 98 spots here, and there's 2 spots that you're not counting, and that's why it's dividing by 2 factorial.
Okay.
It's a simplification then.
What was it?
So it's a simplification then.
It's a yeah. It's a nice way of thinking of it. Exactly. That's right. Okay. And honestly, there's nothing actually very complicated or advanced going on. It just looks like a little bit intimidating with the notation, but it's just thinking about, okay, well, if I only go down this far, then that means I'm canceling out the first two terms because n minus 1, n minus 3 are 2 steps apart. Okay, now we have this formula, n factorial divided by 10 equals n minus 1 factorial divided by 2 factorial. And now I can rearrange stuff. So I'm going to cross multiply because it's a proportion. So I can do n factorial over n minus 1 factorial is equal to 10 over 2 factorial. This is equal to just 5, 10 over 2. But what do we know about n factorial over n minus factorial, n minus 1 factorial? Does anyone see what that becomes? Not exactly. Dimitri, why do you say n? You got it.
Well, I just started thinking about some examples, like 10 factorial minus 9 factorial would just be 10.
Nice.
And you can do that for a bunch of other things. And then I was just thinking, if you take dividing by the factorial right below it is how I was thinking about it.
Yes.
And that's going to only leave the very first term.
Exactly, that's right. So, and that's a nice general thing when you're dividing or taking ratios of factorials, is that always one of the factorials has the same numbers as the other one, just more numbers. So whenever you take the ratio, a bunch of stuff will cancel. So n factorial over n minus 1 factorial, well, this is just n minus 1, and so forth down to 3, 2, 1. But in the bottom is n minus 1 factorial, so that's just that. And then they cancel, and you're just left with n. But we know that that's equal to 5. Okay. That one is a bit harder. But if you can understand that, I think that's great. Somebody asked about number 7. I actually went over that one last time. So again, that is a really important one to understand. I will expect you to know how to do that one for the exam. Please watch the video on that one. Try to kind of follow along with the idea there. If you still have questions, I'm happy to discuss during the office hour. But that one is very, very important. I make sure you understand how it works. And it's not a super easy one either. Number 7, the one with the cars of different colors, how to arrange them. We combined a few ideas there. The idea of the Mississippi problem, the idea of the super letter, and then the idea of the complement. We thought of like, hey, it's actually easier to count all the different arrangements and then take away the arrangements where the yellow cars are together. So I really like that problem. That's one of my favorite problems. Okay, let's do, okay, I just have I want to talk about number 11, just to kind of show an important idea, and then just a little bit about combinations. And number 11 is similar to number 13 and 12. Hopefully that'll give you some inspiration. Oh, the video is in the underneath the class notes. There'll be a link to the video for that day. Okay, number 11 says a crate of 10 cars, 10 working cars, and 4 defective cars. So there's 10 working cars, total 14 cars. The question is, how many ways can 5 be selected if only 3 work? Okay, so I really like this problem because it illustrates the fact that everything is based on the counting principle. This is almost exactly like Billy's problem where he has to pick different outfits. Like remember, he had a certain number of options for his shirt, a certain number of options for the pants, and a certain number of options for his hat. And just multiply those numbers because you can get a tree for each number of options. So this is actually the same problem, except for Billy, it was really simple. I just told you he had 4 shirts. Sometimes when you're doing Billy's, the fundamental counting principle, the number of options that you have to figure out, like inside of a certain category, is itself a mini problem. So I like it because it's a problem, and then a small part of it is its own little counting problem. So it's like a problem inside of a problem. But it's nice because you can zoom out and see the big picture, and that's really just a version of Billy's picking outfits. Okay, so what do I mean by this? What are the 2 categories? Imagine it's Billy who's picking the cars. What are the 2 categories that Billy has to pick? So there's 10 working cars and 4 defective cars, and he's got to pick 5 cars total. What are the 2 different categories?
There's 2 categories.
What are they, Andrew?
Working and defective.
Nice. And in particular, for the working cars, how many does he have? What does he have to pick for working cars? Specifically, like what does he need to pick?
He needs to get 3 working cars.
A group of 3 working cars. And then for the defective, he needs to pick a group of 2 working cars. It's almost identical. Oh, sorry, a group of 2 defective cars. And we're going to just kind of do this abstractly first. Group of 2 defective cars. Now, and Andrew, you can jump in here, or if somebody else wants to jump in, I'll be welcome to. How many ways are there to pick a group of 3 working cars where you don't care about how they're ordered, you just want to know which group of 3 you picked. You just want to count how many groups of 3 there are. And you don't need to give me a number, but what tool could we use to count that? And we'll calculate the number in the end, but what notation do we have to express that? If you have 10, a group of 10, and you got to pick 3 of them, and you don't care how they're ordered. Permutation is part of it, but it's not exactly permutation. If you have 10 cars and it's the one with the C, that's right. It's the combination. It's 10, choose 3. So it's 10, choose 3. Please hit yes if that makes sense. It's like that's the number of groups of 3 cars you can pick that work. And he doesn't care which way he picks them. Okay, based on that, for the category of the defective cars, how many ways are there to pick the 2 defective cars?
Five, choose 3.
Oh, we're only picking 2 of them, but you'll see this actually turns out to be correct as well. It's going to be 5, choose 2. But very good. Well, we don't want to do 7. Only do 5 because there's 10 working and my bad. I'm really sorry. There's 4 defective. So out of the 4, these are the 4 and these are the 10 here. Okay, so now let's calculate this. This is good practice. I expect you guys to be able to do these without a calculator. So I'm going to do 10 times 9 times 8 all over, because there's 3 spots. 3, 2, 1 times 4 times 3 over 2 times 1. By the way, just to remind you, whenever you write the combination symbol, there's no fraction here. It's just its own symbol that we write. Then when you actually calculate it, it is a fraction. Okay, the 3 and the 9 will simplify to a 3. The 2 and the 4 simplify. The 2 and the 8 simplify to a 4. So I get 120 over here. And then over here, I get these cancel to a 2. I get 6. So it is 120 times 6, which is 720. All right. Do you guys have any questions? Is that calculation? Do you feel comfortable doing that calculation? Do you guys see what I mean? That this is like a Billy's problem with the clothing, except it's just a little bit more complicated because the category itself, in each category, you have its own little mini thing that you need to count. So that's why I think of it as a problem in a problem type of situation. But I really like these ideas, the way you can apply all of them. And you really need to have kind of a open mind to see a problem and try to see how the tools you've learned, how you can use those tools to solve it. Because I don't want to just say, okay, this problem you have to do this. This problem solve like this. It's really about kind of being creative with how you apply the techniques here. Okay, I'm going to let you solve number 12 and number 13. They're very similar to number, they're related to number 11. I'll let you guys think about those. Yeah, I'll let you work on the rest of them. Do as much as you can. We can discuss them next time. Also the notes, some of the previous notes that I had, it has some of the solutions as well. So take a look at the notes that I posted. Okay, so I just want to do a quick exercise, then I'll let you guys go, maybe like another 10 minutes or so. So I want to get some practice doing combinations and understanding them intuitively as well. So here's some examples, and this is also from the notes. So please calculate these by hand. It's a really good exercise just to get warmed up doing these. So 5 choose 2, 5 choose 3, 7 choose 2, then 7 choose 5, and then over here 6 choose 1, and 6 choose 6. Oh, sorry, my bad. 6 choose 5, and 6 choose 6, and 9 choose 3. The last ones are a little bit longer. 9 choose 6. Okay, I'll give you guys a few minutes. Please calculate them. Make sure you have a pencil and paper to do these, and let me know what you get. Okay, let me know when you're done. How are you guys doing? Any luck on which ones are you guys on? You could just tell me.
I'm on the fourth one.
Nice. Okay, cool. And let me know if you need some help with them if you're stuck on any of them. Nice. Okay, excellent, Corbin. Excellent. I'll let you guys keep working.
I think I might be doing something wrong. For the first two, I got the same answer, and then for the second two, I also got the same answer. Is that normal?
That is very normal. Very good.
Okay, cool.
That's good. Okay, so I'm going to write out a few of them here, and just let me know if you made a mistake and you want to kind of go over it. This is 5 times 4 over 2 times 1, which the 2's cancel. If you with a 2 here, this is 10. When you do this one, 5, 4, 3 over 3, 2, 1. The 3's cancel, the 4 and the 2 cancel, also gets you to 10. 7 choose 2 is going to be 21. And it turns out that 7 choose 5 is 7 times, you do 5 spots, 1, 2, 3, 4, 5. So 7, 6, 5, 4, 3. And on the bottom, you're at 5, 4, 3, 2, 1. The 5, 4, 3, 5, 4, 3 cancel. The 2 cancels here, leaving you with a 3. And you also get 21. 6 choose 1. That turned out to be 6. This one also, if you calculate it, is 6. Did anyone calculate 6 choose 6?
I got 1.
Nice. Nice guy. Very good. If you actually do it out, you get 1. And then last two. Anyone get 9 choose 3 and 9 choose 6?
I got 84.
Nice, Corbin. Excellent. Did you get both of them?
Yeah.
Perfect. Okay. So let's take a look. I think it was Andrew who mentioned that he noticed a nice pattern that, oh, hey, hang on. These are the same. These are the same. What's going on? Oh, a bunch of these are the same. Does anyone want to volunteer to kind of explain what's the pattern you notice here? Why are they the same? Like, what's the reason? Or kind of what's special about the numbers that's making them the same?
It's because 6 6 over 6 would just be same numerator and same denominator, and that would equal 0.
Well, hang on. For which one? Like, why is the 21s the same and the 10s? What's the common thing?
Oh wait,
with
I
them?
thought you were talking about 6 over 6. So
Oh yes, yes, that's right. 6 choose 6. That's like 6, 5, 4, 3, 2, 1 over 6, 5, 4, 3, 2, 1. Everything cancels.
yeah.
But why are the 10s the same, the 21s the same, and the 6s the same, and the 84s the same? What's the pattern there? What pattern do you notice making them the same?
Yeah, we can tell that it's like because the top and like there's more numbers being added that are being multiplied on both top and bottom.
Good. Okay. And what's in common? 5 choose 2, 5 choose 3. Those happen to be the same. But like if I did 5 choose 1, that wouldn't work. That wouldn't be the same as 5 choose 2. So why in particular are 5 choose 2 and 5 choose 3 the same? And 7 choose 2 and 7 choose 5. Do you want to try some other ones that might be the same? Like how do we know ahead of time that they're going to be the same? What do you guys notice about the pairs that are the same? And it's a very simple pattern, actually. Any ideas? Anyone see it? What about the numbers? Kai, yeah, I think I like your idea. What can you elaborate on that? And be careful. They're not necessarily numerators and denominators, but
Oh, like say it's like, I guess 5 factorial over 2 factorial, or I guess it's 5, choose 2.
Mhm.
I don't know how to explain this.
well, okay.
I guess, sorry.
No. What if it was 10 choose 7? What other combination would 10 choose 7 be the same as? Based on
10
this pattern.
choose 6.
Oh, not 10 choose 6.
Wouldn't it be 10 choose 3?
Nice, Shay. Do you guys see the pattern here? That the numbers, the combinations that are equal, the things that you're choosing always add up to the total that you're choosing from. So 5 choose 2, 5 choose 3 are the same. 7 choose 2, 7 choose 5 are the same because 5 and 2 add up to 7. 6 choose 1, 6 choose 5 are the same. And 9 choose 3 and 9 choose 6 are the same because they add up to 9. Okay.
Would that work for any?
Yeah, so let's investigate that. What do you think? Why is this happening? Is there some reason that this works out to be the same? How could we have, why is it not a big surprise that this works out? Without using math, can you explain why? There's a really, really interesting and simple answer for it. Like, why is 9 choose 3 the same as 9 choose 6? Why do I not even need to do any math to justify that?
Because the lots and the numbers just kind of cancel out.
I would say that's correct, but that involves doing some math because you have to know the fractions and you have to know that there's canceling or whatever. But without doing any math, how can I argue that picking 3 friends, or imagine it's like 9 choose 3 is the same as if you have 9 people and you got to pick 3 of them to join your chess team, right? Why is that the same as having 9 people and picking 6? The number of ways to pick a team of 3 is somehow related to 9 choose 6. Why is that? And there's a very silly but simple, important answer to it. And Dimitri was you kind of said it actually. You have the main idea there. So, yeah.
With the numbers.
Can you say that again? Oh, Alejandro, can you say that again? Sorry.
Numbers, like as in if, for example, if I have 6 friends that I have to choose, there'll be 3 left over, and if I have 3 friends, then there'll be 6 left over.
That's right. Exactly. Every time you pick a group of 3, you're actually like if the coach wants to pick a team of 3, there's 2 ways the coach can do it, right? The coach can tell the 3 students, hey, you 3 students, you're on my team. But at the same time, the coach can be really mean and say, I'm actually going to call up the people and call up 6 people and say, hey, you're not on my team. That's like picking a group of 6. So every group of 6 has an equal group of 3. And so if you're counting the groups of 3, you can just count the other groups of 6 that are not picked. Okay. Does that make sense, that idea? Now that you've seen it, it's actually pretty obvious, right? And it's very useful because sometimes the way I showed you how to calculate combination can be kind of tedious. So, for example, if you want to say if you have 100 friends and you want to invite 98 of them to the movie, 100 choose 98, I wouldn't want to write it all out. What else can I do instead of inviting 98 friends? What's another thing I can do?
Subtract 2.
I can invite or disinvite 2 friends, say, hey, you guys are not coming, everybody else come with me, right? That's a much easier way to do it, and it accomplishes the same goal. So counting the 98 friends to invite is equivalent to counting 2 friends to not invite. And this is much easier because it's 100, the first friend times the second friend, number of options for the second friend, divided by the way to rearrange them. And that I can actually do reasonably. Okay, and the last thing I'll let you guys go. I want to focus on these few. Can anyone explain, without doing any math, why is 6 choose 1 equal to 6? Is that pretty obvious?
Because it's times 1, or there's nothing it's being multiplied by when you're like doing the math.
That's right, but without any math. If I have 6 friends and I want to pick one of them to the movie, how many ways are there to do it? I only have 1 ticket and 6 friends.
Yeah,
Well,
you just choose any one person.
exactly, there's 6 friends. That's it. There's no combination or anything. That one's a simple answer, right? But how about this one? 6 choose 5. If I have 6 friends, but I only have 5 tickets, what am I really doing in essence?
Choosing who you don't want to go.
Exactly. And that's why there's 6 friends that I don't invite. And that's kind of the tie-in to this idea. Okay, the last 2 ideas here. 6 choose 6. If I have 6 friends and 6 tickets, how many ways are there to invite them to the movie? Without math? I just got to invite all of them, right? They all come to the movie with me. And this ties into another one. And this is nice because it doesn't work with the formula really, or kind of the way that I showed you. What if I have 6 friends, but no movie tickets? How many ways are there to do that? What do you guys think? 6 friends, but I have no movie tickets available. How many ways are there to go to the movies?
0, because none of them can go.
So it's not 0. You're right, none of them can go, but we're counting the number of ways that they can go.
6.
Wait, is it undetermined? 'Cause since that would be 6 over 0.
It's not undetermined, and this is kind of a tricky thing, because we're counting the number of ways that they can go. If none of them can go, and let's say I go, right? But I don't invite none of my friends, or that's one way of going is to have none of them go. So it's actually 1. It's related that if I have 6 tickets, it's the opposite event of this. Right? The number of ways to pick nobody is 1. Just don't pick anybody. That's one way of doing it. Just like the number of ways of picking everybody is 1, you pick everybody. What do you guys think? Does that do you feel better with that DCY is 1 and not there's a tricky thing here that I think Kai mentioned is the 0 factorial thing, because you kind of like have a 0 on the bottom. So it turns out that, and this is a bit strange, 0 factorial could be interpreted as 1. So this is where the factorial symbol kind of breaks down. It's the number of arrangements of no objects is just 1, where you don't have any object, you just have nothing. But it's not that we have nothing, it's we're counting 1 way of having nothing. That's what it's all about. All right, guys, have a wonderful weekend. Please do your best on the homework. If you need an extra day or 2, that's fine. And if you don't finish some questions, that's again totally fine. We can keep continuing discussing them on Tuesday. And if you have, take a look at some of the notes and some of the last videos if there were some questions that we didn't get to go over today. You'll be graded on effort for the homework.
Where are the videos for the past few classes?
Yeah, so the videos are always going to be beneath the notes.
Okay.
Like they're like linked with the notes.
Okay, cool. Thank you so much.
Yep. See you.
Thank you.
See you guys. Bye.
Bye, Daniel.
Take care.
Bye. You too.
Mr. Minsky, would it
Yes.
be fine if I had one more day?
Oh, definitely.
To work on it.
Yeah, take your time. If you need to hand in by like Monday or Sunday, that's totally fine. Again,
Yeah.
I only graded. I'm pretty lenient on homework grades. It's really about like trying to do as much as you can, making sure you're keeping up with the ideas,
Mhm.
and then this way you have something to ask about in class. I don't have time to like actually go through everybody's homework and like grade them one by one. So yeah, take your time when you feel like if you need a few more days to think about the questions. I'd really appreciate that. I think that's great.
All right. Thank you very much.
Okay, see you next week.
See you next week.